everyone, welcome to Learning at 11th Hour. In this video, I'm going to talk about state reduction and we are going to discuss initially why we should go for it. Then we'll take up an example and see what are the advantages of going in for state reduction and the various types or techniques that are involved in this. Let's get into the video. So, why do we really need state reduction in digital logic circuits, especially while going for implementation of a circuit from a state diagram? So, if we have a state diagram, what we can do is we can obtain the state table from it, the state transition, and therefore the state table from it. And from the state table, we go for the excitation table, followed by uh, the K map to obtain the expression of the flip flops, and then we go for the implementation. So, this is the design flow for any sequential circuit design. But while we are converting the state diagram that is given to us into a state table or a state transition table, it might so happen that we might use more number of states than is necessary. And that might happen without our knowledge, right? So we can actually give away or do away with such redundancies, and that in turn will help in removing the uh, clutter in our state table. Therefore, there's going to be more clarity in our problem. The state table is going to look smaller. So, therefore, our state diagram would also reduce in size, which means that we are going to require less amount of hardware to represent it. So, having said that, let's look at the various techniques that are involved in state reduction. There are basically three techniques that are there. The first one is called as row elimination method. The second one is called as the implication table method. The third is called the successive partitioning. Today, we are going to look at row elimination method. So let's take up this example that you can see to the left of the screen, and we are going to apply the steps, these 5 steps that have been enlisted here on the right half of the screen, and that would actually help us reduce this state diagram into a simplified non-redundant form. So the first step that we need to do is we need to obtain the state transition table from this state diagram, after which we are going to identify the states whose outputs are the same. So the output behavior is going to be the same. And then we are going to compare these states and see if they are actually making a transition to the same next states for a given input. If it is true, then we are going to combine these states, calling them to be equivalent to each other. And wherever the uh, equivalent state is occurring anywhere else in the state diagram, we are going to replace it. So this is going to repeat until there is no new state that is available that can be combined. So this is going to be really clear only when we try and work it out. So let's see how to go about this problem. So here we have the state diagram that we had taken up as the example. The first step was to obtain the state transition table. So here in the state transition table, what we have is we are going to have the present state, then we are going to have the next state pertaining to the input x, because we can see that there's just one input involved over here, and this is actually the output. So if x is my input and say z is the output, so there's just one input and there is just one output, and we see that the output is dependent on the inputs. This is actually a mealy machine. So this is going to be the output z, and it is going to vary with respect to x is equal to 0 or 1, the external input, and ns stands for the next state. X is equal to 0 and 1 are the inputs for which the next states would vary depending upon what the present state is. So here we have states a through f. So let's enlist them first: a, b, c, d, e, and f. Now they are going to make a transition to the next state depending upon the input x. So when x is equal to 0, what happens to the next state, right? So let's analyze each state one at a time and then consider the two different possibilities of the inputs and then see where they are going. This is a very simple step. So let's take up one state at a time. Let's look at state A. When the input is 0, the transition goes back to the same state. So it remains in the same state. The output in this case remains 0. But when the input is 1, then from state A, it makes a transition to state B and the output remains at 0. Let us now move on to state B. In state B, when the input is 0, then it makes a transition to state C and the output remains 0. For state B, when the input is 1, it goes to state D and the output remains 0. Let's look at state C. From state C, when we get an input as 0, it goes to state E. The output remains 0. And for 1, it goes to state F and the output remains 0. Now let's move on to state D. For state D, for 0 input, it goes to B. The output is 0. From state D, for input is 1, it goes to A and the output is 1 over here. For state E, if you look at state E, for 0, it goes to state C with an output of 0, and for input 1, it goes to D with an output of 0. Finally, state F. For state F, when the input is 0, it goes to B, the output is 0, and for 1, it goes to A, and the output is 1. So this is the first step where we have formed the state transition table. The second step is to identify the different rows for which the outputs are similar. So if you note carefully, for say D and F, the outputs are 0, 1 in both cases. Having identified such rows, we now have to look at the next state of both these rows and compare them and see if they are equal. So in this case, if you see, F makes a transition to B and A for x is equal to 0 and 1 respectively, and D also makes a transition to B and A for x is equal to 0 and 1 respectively. This basically implies that state D is equivalent to state F. So there is no point in retaining both of them. That would be redundant. So I'm going to remove F or eliminate state F, and wherever F is going to occur, I have to replace it with D. So now we have this reduced state where there's just one state that has been eliminated. Let's move on, and we see that the remaining states, state A, B, C, and E, they all have outputs 0, 0. So we can now compare and see which of these are actually equivalent. So if we compare E and C, E is moving to C and C is moving to E for x is equal to 0. And uh, they are moving to D for x is equal to 1. So for x is equal to 1, both of them are making the same transition. But for x is equal to 0, we see that they are actually going to the other state. For example, if it is state C, it is going to E. And if it is state E, it is going to state C. So this means that it is going to satisfy the condition of tautology. So the example for that is, for example, I can say uh, either x is equal to y or x is not equal to y. So this is, say, my condition. Now what will be the status of this condition? So these are the only two possibilities for x, right? Either x can be y or x cannot be y. So both these conditions uh, either one of them are going to exist. So this means that this condition is always going to be true. So that means this is going to satisfy the condition of tautology. So either C is going to be E, or E is going to be C. In either case, they both are going to be equivalent. And for x is equal to 1 also, they are making a transition to the same next state. So therefore, we see that we can actually eliminate one of these and retain the other. So wherever we see the state E occurring, we can replace it with C. So now let's observe, let's rewrite this because it's too cluttered. So suppose I have A, and then I have B, I have C and D here. So for next state and for the output, what I have is A, B, 0, 0, C, D, 0, 0. And for C also I have C, D, 0, 0. And for D, I have B, A, 0, 0, 1. So here we can now again continue, right? So here if you see the state B and C, they have the same output behavior and their transitions to the next states is also similar. So therefore these two are also equivalent. So we can say B is equivalent to C. So therefore let's eliminate say C, and wherever C occurs, I am going to replace it with B. So ultimately what I have is I have only three states, A, B and D. So this is state A. The next states are A, B, 0, 0, state B, B, D, 0, 0, and state D, B, A, 0, 1. So this is my updated state transition table that is in its reduced form. So from this, when I try to draw the state diagram, I have state A, I have state B, and I have state D. So for x is 0, it is going to remain in the same state. The output is 0. For x is 1, it is going to go to state B, but the output is 0. Let's look at state B. For x is equal to 0, it will remain in the same state with output 0. For 1, it is going to go to state D with output 0. Observing state D is going to go to state B. For x is 0, but the output is going to be 0. And it is going to go to state A for x is equal to 1, and now the output is going to be 1. So this is now called as the reduced state diagram, and state reduction forms the first step in the design of synchronous sequential circuits, wherein we actually obtain this reduced state diagram from which we can go for the state transition table, the excitation flip-flop excitation table, and then flip-flop implementation. So I hope the concept of state reduction is clear to you all using row elimination method. In the upcoming video, I'll tell you how to use the implication chart to arrive at the reduced state diagram. If you have any queries regarding state reduction, please do not hesitate to post them in the comments below. Thanks a lot for watching.